Hello scholars, welcome to two sample significance test for proportions, section 9.3. This is for P1 minus P2. For these hypothesis tests, usually there's a test that there is no difference in the two samples. And for that, H naught is usually P1 minus P2 equals 0. That can also be thought of as P1 is equal to P2. However, we normally write it this way, where P1 minus P2 equals 0, which means the same thing. But that way we can have our distribution centered on 0 and use a z-score and z-distribution for that. You have three possibilities. The possibilities for one-sided is that P1 minus P2 is greater than 0. Notice that means positive integers. So if that is our HA, then we're expecting P1 to actually be bigger than P2. When I subtract them, I would get a positive integer. Other possibility is P1 minus P2 is less than 0, means we would get negative values. And if we have negative values, that means that P1 is actually smaller than P2, so we would get negative numbers. And when we do that, our z-score, we should get negative values for this HA and positive values for that HA, and that will become our p-value when we find that area. The other possibility is that we have a two-sided alternative hypothesis, which means P1 minus P2 just doesn't equal 0. So it could either be positive values or negative values, which is the same thing as just P1 just doesn't equal P2. The conditions for a two-sample z-interval for proportions is the same as the conditions for a two-sample confidence interval for proportions. So you have your random, independent, and normal or large counts conditions. So for randomization, you have to have data that comes from two separate well-designed random samples or a randomized experiment where the subjects are randomly given two different treatments. Independence, if you sample without replacement, you have to have capital N sub 1 greater than or equal to 10 N sub 1 and capital N sub 2 greater than or equal to 10 N sub 2. Sometimes with experiments, you don't have to check those if it tells you that the subjects were randomly placed, because usually one subject has no effect on the way a drug works or whatever you're studying works on another subject. So that is another way that you can test independence. Then the normality counts, again, are the same as they have been. You have to test all four of those normality or large counts. Okay, so the test statistic that we have for this test still follows the same generic test statistic that all of our hypothesis tests have followed, where I have my statistic or my sample value I get minus the hypothesized parameter divided by the standard deviation of the statistic. So in this case, we end up with P1 minus P2 hat, which is our statistic, minus P1 minus P2, which is from H naught. And we'll talk about the bottom, what PC sub hat means, in a second. Normally, if my H sub 0 is that P1 minus P2 equals 0, and since we're assuming that that's true, then what happens is this whole thing, the P1 minus P2, gets replaced by 0. So those values actually all become 0 when you do a hypothesis test. Okay, so what is PC? So PC sub H is, or PC hat, is the pooled sample proportion. Now we only use pooled sample proportions, pooled estimates for proportions, not for means at all. So when we get to averages and hypothesis testing for averages, we will not use the pooled values. So make sure that you know the difference. So basically it's just my total number of successes divided by both my samples combined. So I take both my success numbers from each of the sample, add them together, that becomes the numerator, and both of my sample sizes, add them together, that becomes the denominator. So it's as if you were putting both sets of samples together as one large sample, one pooled sample. And basically you would calculate the proportion of successes in that total pooled sample. So that goes into the test statistic given on the slide before. Okay, so here's an example problem we're going to do. So high levels of cholesterol in the blood are associated with higher risk of heart attacks. Will using a drug to lower blood cholesterol reduce heart attacks? The Helsinki HERE study recruited middle-aged men with high cholesterol but no history of other serious medical problems to investigate this question. The volunteer subjects were assigned at random to one of two treatments. 2,051 men took the drug gemfibrozil to reduce their cholesterol levels, and a control group of 2,030 men took a placebo. During the next 5 years, 56 men in the gemfibrozil group and 84 men in the placebo group had heart attacks. Is this difference statistically significant at the alpha level? So basically we need to get out of here all the information that we need. So this looks important, this looks important, this looks important, this looks important. So we're going to our template to fill out where we can find information that we know. Okay, so I know that from the first proportion, I'm looking for the men that took the gemfibrozil and the proportion of them that had heart attacks. So my P1 is proportion of men that took gemfibrozil and had a heart attack. And P sub 2 is going to be the proportion of men without gemfibrozil that had a heart attack. Okay, so that means capital N sub 1 is not a known value. Capital N sub 1 is going to be all the middle-aged men, so the number of middle-aged men that took gemfibrozil. And N sub 2 is going to be the number of middle-aged men that did not. Little n sub 1 is our sample size for our first group, and that's 2,051. Little n sub 2 is from our second group, 2,030. X sub 1 from our first group was 56. That's our number of successes. Now in this case, our number of successes is actually the number of heart attacks, which doesn't sound like a success, but that's what we're calling our successes. So P1 hat is going to be 56 out of 2,051. which is 0.0273. And P2 hat is going to be 84 out of 2030, which equals 0.0414. Now for this problem, we are also going to need a PC hat. So the PC hat is all of our successes over the entire sample size. So it's going to be 56 plus 84 over 2051 plus 2030, which ends up being 0.034. So that's our PC hat, and you'll see later where we need that. We need that in our Z statistic. So we're going to conduct a two-sample, one-sided significance test. It's a Z test for proportions, specifically a difference of proportions, because it's a difference of two proportions. And the alpha level this time was given to us in the problem. It's 0.01. H naught is that there's no difference between taking gemfibrozil or not. So that would be that P1 minus P2 equals 0. And in this case, we actually want the gemfibrozil group to be lower than the non-gemfibrozil group because we want to see if the drug works. So we want to get values that are negative numbers because we want P1, the gemfibrozil group, to have a lower proportion of heart attacks than the non-gemfibrozil group. So that's why our HA has a less than 0 to get that negative value. So pause the video here because the next step is to check conditions. And I want you to try to check all the conditions on your own, and then you can see if you got them right. So pause for a moment. Okay, here are your conditions. Check. Hopefully you got them right. Notice that with the independent check, because this is an experiment, you can actually assume that it's independent because one person having a heart attack has no effect on the other subject's likelihood of having a heart attack. Or you can use the formula, but for experiments like this, you can just assume independence. Okay, so now for the do. So your test statistic. We have Z equals P sub 1 hat minus P sub 2 hat minus P sub 1 minus P sub 2 over the square root of P sub C hat, our pooled value, times 1 minus P sub C hat, all over N sub 1, plus again P sub C hat times 1 minus P sub C hat, all over N sub 2. So that is going to equal 0.0273 minus 0.0414, and this value right here is all going to equal 0 because my H sub 0 is what I'm assuming to be true. So H sub 0 is that P1 minus P2 equals 0. So technically I have a minus 0 here, but I don't really even need that. Just stick with what you got. So this is over the square root of, now don't forget this is using the pooled P sub C hat, 0.034 times 1 minus 0.034 all over N1, which is 2051, plus 0.034 times 1 minus 0.034 all over 2030. Really make sure that the square root sign covers that entire mess on the bottom and that you put enough parentheses in when you do this. If you did it correctly, you should get a z value of about negative 2.47. Okay, so that's our z, and since we have a z statistic, this is going to be normal with 0 as my mean and 1 as my standard deviation. So 0 is in the middle, so negative 2.47 means I am 2 standard deviations below the mean, and my area here, if I use my calculator command, I'm doing the normal CDF. My lower bound will be negative infinity, because remember that's on the left, and my upper bound, so I can use 9s in my calculator, my upper bound will be negative 2.47 with a mean of 0, standard deviation of 1, and what I get is my p-value, which is about 0.0068. So check these calculations on your own, see if you can get all of the same numbers, the z value and the same p-value. So that p-value appears very low, and we know what that means. That means I'm going to probably reject. That shouldn't be surprising because I got a very low z value, so I'm over 2 standard deviations from the mean, which means I'm far away from the normal, from the mean. Okay, so we're going to go ahead and write our conclusion now. So use your template for writing the conclusion. In the conclusion, I'm going to say assuming H naught is true, and in parentheses you can say something like P1 equals P2 or P1 minus P2 equals 0. Let's make this bigger. So assuming H naught is true, there is a 0.0068 probability of getting a difference in sample proportions equal to and there's where we would put in our actual sample proportions, which is 0.0273 minus 0.014, which equals negative 0.014. So notice we got on the negative side, and that's what we were hoping for, to show that the Jim-Fibersole proportion is actually smaller. So or less purely by chance. Okay. Okay. This is strong evidence against H naught and is statistically significant at alpha equals 0.01 because the p-value of 0.0068 is less than alpha. Therefore, we're going to reject H naught. So therefore, we reject H naught and conclude that there is convincing evidence that gemfibrozole helps to reduce heart attacks. In middle-aged men with high cholesterol. So make sure you include what types of subjects, if there's a specific type of subject that was in the test. Because we wouldn't be able to say that these findings necessarily worked for subjects that were different from the test subjects. All right, and that's it. That's our beautiful conclusion. And just because it's close to Valentine's Day, I end here with a nice cheesy Valentine's statistics line for you. I don't need to look at more data. What I'm feeling with you is already statistically significant. There you go. You can use that one. Have a great day.